Last time we were talking about solderability and pretty much finished it up, unless you have some questions. Mentioned that solderability testing is empirical. You just basically kind of dip it in and measure the time it takes for the solder to wet. We also mentioned that if you go through the dimensional analysis, solder drops below 3 millimeters or 1/8 of an inch, surface tension forces will start to dominate. We also mentioned that solder composition must be closely controlled, and we didn't mention that I have to travel this week, and so we have class tomorrow, but then the next class would be the next Wednesday because I'm gone the last 3 days of this week, and I'm going to give you Monday and Tuesday as a holiday next week. Okay? Just, isn't that nice? Well, that's partly because I'm going to be traveling those 2 days too. But I will be back on the 10th, and I think next week we only have 2 classes because it looks like on the 11th I've got to be in Washington. But we will have class on the 10th and 12th. Right now it looks like we'll finish up about October 25th, unless something else comes up that I have to go to. Okay? So, well, I guess I can throw that one up. This is the reason you start with the middle board, because if you throw it up, it's still there for the students to copy. Brazing. Brazing, we mentioned before, is just soldering, but it occurs at a higher temperature. Older books say 425C, newer books say 450C. It's an arbitrary number. It doesn't really matter too much. That's 800 to 840 degrees F. But because we have higher temperatures, it means there's a greater flexibility in the choice of fluxes. In the solder fluxes, we tend to use organics, like oxalic acid or rosin, or we use, well, actually, that's mostly what we use. It's not too often we really use salts. We use some aqueous salts, like zinc chloride in water or tin chloride or something like that. But when you go to brazing fluxes, you now can use actual salts, anhydrous salts, such as zinc chloride or tin chloride, or even some of the fluorides or fluoroborates. And because you can use these much more aggressive salts, you basically end up with reactive fluxes that can scour that surface and basically reduce almost any oxide. In fact, I don't know of any oxide or sulfide that can't be reduced. I've never come across a base metal or even most non-metals, ceramics here, that can't be brazed. In fact, on the first day of class, I didn't really tell you that in general, I say that you can bond virtually, you can join almost anything if you're willing to pay the price. And I mentioned that joining is ubiquitous on that first day. And not just in being able to braze most materials, but you can either weld or solder or braze or adhesively bond together almost anything if you're willing to pay the price. That doesn't mean you can always do it in exactly the geometry and not degrade the base material properties or do it by a specific process. But there's not very many things that I've come across that can't be joined. There may be constraints, other constraints, that make it so you can't do it very easily or very cheaply. But if you're willing to pay the price, you can usually do it. In brazing, you can almost always find some flux that will work. Whereas in soldering, we had certain things like titanium and zirconium that couldn't be brazed, couldn't be soldered, because there was nothing to eat away the oxide. The room temperature strength of the filler metal is also greater in brazing, even though it's just a temperature difference. And that's because you're going to be above some significant value of the, you're going to be below a significant fraction of the absolute melting point. Remember, you have problems of creep with the solders, because the solders, if we use 6/10 to 8/10 of the absolute melting point as the creep regime for the material, when we talked about diffusion bonding and stuff, well, if you talk about solders that melt at 200 degrees centigrade, you add that to 275. 275 or 273 Kelvin, and you get 473 Kelvin. Basically, room temperature is about 300 Kelvin. and you're at 6/10 of the absolute melting point just at room temperature in most solders, the solder that melts at 200 degrees centigrade. So you have a problem here with the solders, and they're going to be in a creep regime at room temperature. And as a result, you really can't use solders for strength designs above about 1,000 psi. In fact, you're really pushing it for long term for solder alloys. In the old days, the sprinkler systems basically had a solder connection that would melt at 175 or F or something like that, and that would allow the sprinkler system to open when it felt the heat. Well, the problem with that is some of these things were in service for 30 years and they just decided to let go because of creep. So they don't do that anymore. Anybody know what they use in most sprinkler heads now? Those little bulbs, yeah, little glass bulbs. Yeah, okay. If you look in a modern building, the sprinkler heads will have a little glass bulb that has got a fluid in it. And as they carefully meter this closed bulb and the amount of fluid they put in there, and as the fluid expands, as it heats up and the fluid expands, it basically goes hydraulic eventually. I mean, it's got a little pneumatic airspace there, and it's compressing, but when it finally gets to the temperature that you want it to break at, it goes hydraulic, and at that point, a few more degrees, and you put stress on that glass, and it just shatters. The only problem with those types of bulbs is that the glass is brittle, and every now and then, you know, I don't know if it's 1 out of 1,000,000 or 1 out of 100,000 or what the numbers are, every now and then one of those will just decide to fracture on its own without any temperature. The good news is it shatters all over everywhere, and no one can ever prove that it was a defective bulb. Okay, that's true, believe me. Brazes, on the other hand, since you're at above 425 C and you add 275 to that, you get 800, and then you talk about 300, you're below 6/10 of the absolute melting point in most cases. And so you're not really in the creep regime for the braze alloy, and at room temperature you can get 5,000 to 10,000 psi. To compare those numbers with adhesives, typically adhesives you may only get 100 to 500 psi as a bond strength. Remember, adhesives, we said you need lots of surface area. That's because the adhesive strength is not so great. And you can also look at it and say, well, that's because this is actually a metal-metal bonding, failure by creep. This is a metal-metal bonding without failure by creep. And adhesive is a van der Waals bonding because of the contamination left at the interface. Another problem, or a problem with brazing, because not all these are problems, these are features of brazing. You can often get volatilization of the alloying elements, either from the base metal or from the braze metal. One element that has a fairly high vapor pressure is zinc, and another one is magnesium. Magnesium boils at 900 degrees centigrade or something, and zinc melts at 781 C or something. No, 409 or something C, which is like 781 Fahrenheit or something. In any case, they have relatively high vapor pressures, and you can actually get special brazing alloys. The silver solders, the American Welding Society designates a brazing alloy with a B, clever thing for brazing. And if it's a silver solder, it's BHE, AG for silver. So we call these the bag alloys. But so there's bag 1 and bag 2, very clever designation here of these things. But some of these will have a V after the end. Okay, and I don't know, I think there's a 21V. And V means it's specifically designed for vacuum brazing. It has very, very low amounts of zinc or other things in it. A lot of the silver-based brazing alloys have zinc. The bag V alloys have very low zinc. Because you don't want the zinc coming off in your furnace, because the zinc then alloys, we also have copper alloys, or B copper phosphorus alloys, for example. So B cup alloys, okay? That's just the way the American Welding Society designates these things. But some of them have very low zinc content. or magnesium content in some of the the aluminum brazes, very low magnesium, so you don't get these volatiles off and have them react with the windings of your furnace and short out your furnace, okay, because the zinc will form intermetallics with the furnace windings. Another problem with the vaporization of alloying elements, a lot of the silver solders in the past have had cadmium, and cadmium is a toxic metal, and so they've done a lot of work over the years to try to eliminate cadmium from brazing alloys. They haven't really completely done it. In fact, you know, the Europeans are very, very environmentally conscious, and the Swedes in particular are very concerned about the environment, and so they decided to eliminate cadmium from the world. Okay, so they said, well, we're not going to allow cadmium to be used in anything. They passed a law to that effect. Turns out the light switch is a silver cadmium oxide alloy. It's see, I turn the light on. There's 10-15 amps going through there. If it was just a silver contact on that light switch, then you might only be able to take 5 or 10 amps. But if you want a 15 or 20 amp switch, you've got to have something that will, when you click the light off, you won't be able to get an arc. As the contacts separate, you don't want it to continue to arc, because then it'll just kind of melt everything and start a fire. It turns out that for whatever reason, and people have studied this for 40 years, if you put 1% cadmium oxide in with the silver alloy, you can tolerate separations of the contacts at about double the current as if it was just a pure silver alloy. If you start getting up to 40 or 50 amps, you have to start playing different games with the contacts, and they go to silver tungsten contacts and things like that. But for general light switches like that, usually you have silver cadmium oxide. Well, the Swedes about 15 or 20 years ago decided cadmium was bad, and they banned it from anything. And then they started burning down houses, and they just had to modify their law, as I understand it. So they decided to let cadmium oxide back into the switches. Now, how much cadmium comes off when you actually, well, flick a light switch? I mean, it's probably parts per exotrillion or something. You know, I mean, or you know, picotrillion or something. There's almost none that comes off. But people are just worried because they hear the word. Okay, then it hasn't been quantified for them, and they're just very concerned about it. If you're in vacuum brazing, it can be a volatility's problem with cadmium, just a regular brazing. I mean, if you went and right now, they still have cadmium silver solders, but they tend to only use them in an automated situation where they have good ventilation and no people around. You can get enough cadmium off to actually, if someone's doing this for 20 years, start becoming toxic if they don't have good ventilation. Zinc is another problem in some of these things. It can also be in the base material. Some of the brasses, if you go, the brasses can give off zinc, and you can get dezincification. Potentially it's cheaper than welding. You mean for piping systems? The main reason in piping systems is probably when you're going from one material to another material. You can't weld some of the nickel copper alloys, the Monels, directly to steel. Okay, so you're going to have to braze them. If you're going steel to steel, you'll probably weld it. If you're going Monel to Monel, you'll probably weld it. If you're going Inconel to Inconel or titanium, you can't easily weld titanium to steel, so you might braze that. So it depends. It's usually, brazing is commonly used for dissimilar metal systems because you're not melting either of the base materials. And some base materials are not compatible with fusion welding. I mean, you mix iron and titanium, you get iron titanium intermetallics, which are brittle, which is one of the problems down here. The next one down. Okay, so if you're thinking of submarine or seawater piping type stuff, most of the brazing is because you're changing alloy systems. Other questions? So volatilization from the base material or the braze alloy can destroy furnaces, it can destroy people. Cadmium, zinc, and magnesium are the most common things that you have to watch out for. Intermetallics may form during brazing at higher temperatures, and it turns out that we talked about the situation where we had molybdenum and nickel. I talked about the transient liquid phase diffusion bond joint where they were using gold nickel braze alloys, and they got very low ductility in those cross-field amplifiers. That was basically a brazing process. Intermetallics made the joint brittle. And at higher temperatures, we have that occurring a lot more often. It's not to say you don't have intermetallics sometimes in soldering, but you have a lot more in brazing. Thermal stresses can be severe. We've talked before about the fact that 300 degrees centigrade is all you need to reach yield level residual stresses in most things. Well, actually, I did it once before. If I have the strain, thermal strain, is equal to the difference in thermal expansion between two materials times the difference in temperature. If this is 200 degrees centigrade and this is 10 to the minus 5, the thermal strain is 10 to the minus 3. 10 to the minus 3 is 0.002. That's the yield strain for most metals. Okay, 0.2% offset is 0.002. Okay, so it only takes 200-300 degrees of temperature variation between two dissimilar materials to end up with residual stresses that can be up at the yield level of the metal. So you don't have that in soldering because, well, you've got creep going on at the high temperatures, and it's only when things get below the creep regime that you start getting really big residual stresses. But in brazing, I have high enough temperatures to do that. So thermal stresses can be severe. Finally, erosion of the base metal may occur. Because you're at higher temperatures, there's more potential for interdiffusion, alloying between the brazed metal and the base metal. Sometimes in aluminum alloys, you can erode away something a millimeter thick of the aluminum base metal if you put too much braze on, or you have the wrong braze alloy. Now, sometimes it gets even more severe. You want to really reduce the erosion of the base material to a few tens of microns. One particular application is in turbine engines. For the seals between the rotating and the stationary parts. You know, if you think of a turbine engine, you've got three basic parts. You have the compressor, well, you have a shaft going down the center, and you have a compressor with blades on it. So here's your compressor, and then you have your burner, and then you have your turbine, which also has blades. Now, why do you have a compressor? The compressor is compressing the incoming air from about 1 atmosphere, unless you're way up there high, it might be half an atmosphere, but let's say you're down at sea level. You got 1 atmosphere, and you can compress it to about 30 atmospheres. And then you take that compressed air and you burn it, just shoot your jet fuel in here, and those hot gases shoot out the back. If you're trying to propel an aircraft, you use that thrust. If you're trying to generate electricity, you have a bunch of turbine blades. So, in fact, you may even pull a vacuum on the backside. Okay, on a commercial electrical turbine, ground-based electrical turbine, you get more power out of it by pulling a vacuum and have that extra expansion into a vacuum. You actually can pay for the vacuum with the extra energy you get out from the expansion. But in any case, as the hot gases are going past here, they are spinning that turbine. Well, at both locations here, between the walls, I need some sort of seal. And there's different types of seals. But in one application, the reason you need a seal is because this is nothing more than a fan, and you can have, if you didn't have a seal, the higher pressure, you got a higher pressure here than there, and you'd have backflow, and that you can degrade efficiency of the turbine. You can have a big degradation in the efficiency of the turbine, 10% or more if you're not careful. If you want to get those last few percent out of a turbine or a compressor, you want to put seals in here. One type of seal is to take thin nickel-based superalloy foil, this would be foil like 2/1000 of an inch thick, and make a honeycomb structure. and essentially let these turbine blades, as they grow and creep, they grow in length at over time. They get hot and they stretch. Typically, over the life of a turbine blade, you might get 2 or 3% stretch. So if one of these things is 4 inches long, 2 or 3%, you're getting 10 to 15 thousandths of an inch. Well, you can't leave an extra 10 to 15 thousandths of an inch for the gases to leak past and lose all that efficiency. You want to have a seal that is pliable, that will maintain the seal. So basically, they make a honeycomb foil. So the honeycombs are kind of the cells of the honeycomb are facing down like this, and the turbine blade just cuts right through the honeycomb. I mean, you know, the turbine blade's not going to be stopped by 2 thousandths metal foil. It just cuts through it over time, and as it grows, it cuts deeper and deeper into it. Well, you have to, how do you make these honeycomb seals? You basically braze them. However, if it's only 2 thousandths of an inch to begin with, and I've got basically, this is the thin foil, or this is the base material, and I have a thin foil like this, and I want to form a little fillet of braze alloy in there, I certainly don't want it to erode that nickel-based superalloy by 1 or 2 thousandths, otherwise the whole thing's just going to melt and fall apart. So it turns out they used to use gold, 18% nickel, the same type of stuff I was talking about before. So it's 82 gold, 18 nickel. And that forms a low melting alloy. Turns out that wets the nickel-based superalloy with no erosion whatsoever. And that's great. The only problem is this kind of gets a little pricey. An 80% gold alloy that I'm brazing with. A little over 20 years ago, I was asked by a company to come in and do a review. It's actually a military engine project. The problem was they used to this guy was brazing these seals, and production had gone up, and he used to go and get a 50-ounce jar of this braze alloy about once a week. Now, 50-ounce jar, all he had to do was, he had to sign it and his boss had to sign it, the requisition. You go to the stock room and get a 50-ounce jar. 50-ounce jar is $16,000 worth of gold. It's about this big, you know. It's only 3 pounds, right? 3 pounds of gold, big deal. Actually, it's only 8/10 of 3 pounds, so it's only 2.5 pounds of gold. And so he'd go and get this little jar, and they had a little salt. This is how they applied it. They had a salt shaker, and they would take some Krylon crystal clear paint, okay, and the guy would shake the braze alloy into this little honeycomb structure, and he would paint it with Krylon, which would hold the braze alloy in place, okay, and then they'd stick it in the furnace, and the Krylon would burn off, and the gold would start to center together, and it would finally melt and form a nice little braze, and we shipped the part. Well, production started ramping up, and it turned out he really couldn't do all the work he needed to do with 1 jar a week, so he started requisitioning 2 jars a week, and his boss to sign off on it. Well, as time went on, and production started to ramp down, and rather than just getting one, you know, cutting back to 1 jar, he thought, I'll still get 2 jars, 1 for me and 1 for the company. Okay, and the question was, how much braze alloy had he taken out of the plant? And the only reason they caught him is because someone turned him in. He could have still been doing it today if, for all the security they had at that time on this gold alloy. By the time I got there, they're weighing the jar before making up the part, and weighing it afterwards. They were still sprinkling with a salt and pepper shaker, but they were weighing before and after, and they had a little log for each part number. Okay, so they knew exactly how. So it would have been hard to all of a sudden start using double the amount of gold on one of the parts. But before that, they didn't have much quality control. It was just someone shaking a little gold on something. But the interesting thing about it is, I think I estimated he had taken out about $1.5 million worth of gold. When it was all done, he ended up getting, well, the guy in New York that was receiving the stolen goods and, you know, the fence, you know, fencing it, he got, I think they he was scot-free. They weren't able to nail him at all. The person who was running it to New York basically got a suspended sentence, and the guy who made $1.5 million in 1978, or actually he didn't make the $1.5 million, he got a year in prison. Okay, Now, someone has to start asking yourself, is it worth a year in prison, you know, for $1.5 million, given the fact that they never recovered this stuff, because it's very easy to get rid of a gold alloy like that. In fact, it'd be very easy just to dissolve it in aqua regia and precipitate it out, or dissolve the gold and then precipitate it out and sell it as pure gold. But in any case, since then, when gold went up to $800 an ounce, they decided it was getting kind of pricey, and so they've basically gotten rid of this alloy. They developed other alloys. First, they went to palladium nickel alloys, and then, which is at that time was cheaper than gold. Now it's more expensive than gold. And eventually, they got all the precious metals out of these things, and so they don't make the turbine blades that way anymore. But they used to, and it was all because of the erosion problem. They didn't have other alloys that were erosion resistant. Now, any questions? The next thing I want to talk about, when we were talking diffusion bonding, I talked about contact strengthening. And I told you that we would explain it when we got to things a little bit later. Well, now's the time to explain it. Contact strengthening occurs, and we did it when we talked about diffusion bonding with silver interlayers in maraging steel. And so you had a very thin layer of silver between high strength steel, and this was 180 KSI steel. This is 10 KSI roughly pure silver, but when you pulled this thing with tension, you got about 100 KSI strength. And the story goes that the chain is as strong as its weakest link. Why didn't this thing fail at 10 KSI? The reason it didn't fail at 10 KSI is because of contact strengthening. But to give you an idea, it basically has to do with the thickness to diameter ratio of these joints. But this comes out of the brazing handbook. This is the tensile strength. This is the ultimate tensile strength of pure cast silver, which is about, they've got 15 KSI down here. And they show that as the joint thickness gets thinner and thinner, go from 10 mils to 1 mil to a tenth of a mil to something down here at about less than 1 mil, the strength of the joint is over 100 KSI. This is basically the same type of data as O'Brien, Rice, and Olson, but it's not their data. But basically, as the joint gets thinner and thinner, the strength goes up. Eventually, the strength goes back down, and that's because of defects. When you start getting joints that are less than 10,000, less than a tenth of a thousandth, you're talking now less than a few microns, less than 5 microns in thickness. Now you're getting into surface roughness problems and defects in incomplete joints. So this is back down to defects. This is basically contact strengthening in here when you are at these thicker joints, but it's still fairly thin. 10 thousandths was the high end of that. 10 thousandths, yeah. 0.01. 1/100th of an inch. It turns out that if I pull this out, you should have handouts, these handouts somewhere in there, if I can get this guy out. Okay. Well, that's kind of old. I have to redo that overhead someday. I only made this 10 years ago for a talk there, 1992 for a talk. So here's my thin joint, and it has height h. And if I want to do a balance of forces on this little volume element, and I'm pulling in tension with sigma yy, this is my xy coordinate system, and this width of this thing is, well, that's not supposed to be right. That's supposed to be dx is the full width of this thing. You basically are going to put this thing, because the material is constrained by the non-yielding material on either side. This wants to deform, but it can't. It's bonded to the non-yielding material, and you're basically going to introduce a state of triaxial stress in this. Does that make sense? Okay, because you're pulling on it, sigma yy. It wants to contract, but it can't, and so it has, in effect, a tensile stress in that direction. So I've got, if I look at that, I've got tension in all four directions, or all four directions of x and y, plus and minus, and that's going to be equivalent to a triaxial state of tension. So I end up generating triaxial stresses in here. It turns out that if I solve, this is the one place I told you I'll solve a differential equation. Okay. Actually, I don't think I've written down the differential equation. Let me write down the differential equation. Okay. So I take this little volume element with dx, sigma yy, and I have across here a the force in this direction is going to be proportional to sigma yy. It's sort of like a frictional force. So I'm pulling normal, and I'll have a shear stress in that direction resisting this thing because of the bonding on the surface, and that's eta sigma yy going both those directions. I'll have a sigma xx plus d sigma xx times the height of the joint, and over here I'll just have sigma xx. So there's a gradient of sigma xx as I go from the outside edge, where there is no sigma xx, 0, out to the center. There's going to be a high value of sigma xx because of all the stacked material beside it. And so if I resolve the forces in this direction, in the horizontal direction, I have 2 eta sigma yy dx. So that's these two. So it's dx times the stress on there in the horizontal direction equals d sigma xx times h, which is basically the difference between these two. So I've basically summed up everything in the horizontal direction. And well, by sleight of hand, I say that these forces are smaller than those forces. The eta is smaller than, well, eta is small, something like 1/10 or 2/10. And therefore, you can say that d sigma, these are principal stresses, and if that's true, that d sigma xx is equal to d sigma yy, if these are principal stresses. They're not exactly principal stresses because I do have a shear stress there, but they're close to being principal stresses. If I do, and I'll show you a more circle solution to all this, if I do all that, I end up with d sigma yy over sigma yy equals 2 eta dx over h. And if I integrate that from, well, I'll integrate it over here, so I'll have to write it again. I integrate that from x is equal to minus r to 0. So I'm going to go from one edge to the center. I will end up with sigma x, oh, and the dy is going to go from 0 to tau, the shear stress of the material, tau y, sigma x over 2 tau y, oh, I'm sorry, sigma yy over 2 tau y equals e to the 2 eta x over h. Okay? So that's the solution to the differential equation. I've done it. Okay? I did it pretty sloppily. It just has to do with my attitude about solving differential equations. But if I go to the Mohr circle, which is easier because the Mohr circle is just a solution of that same equation. Basically, if I look at a volume element right here at the edge, the Mohr circle for that is sigma yy. You have Poisson's ratio, so this is 0.3 times sigma yy. I can draw the Mohr circle, and I can figure out what the shear stress is at this coordinate system, and that number is almost the same as that number, which is why I can say these are almost principal stresses. If I go to somewhere intermediate, I'm basically just moving this Mohr circle out here. I'm not changing the diameter of the Mohr circle. I'm just moving it out on the hydrostatic stress axis in the tensile triaxial stress. If I go to the very center, it comes way out here, And it turns out the yield strength of the material now is an exponential. So it starts at 2 tau y, and it increases exponentially to the center. So this is if the material was just yielding at 10 ksi, but now I have to add on this triaxially constrained material. And if I do that, I can end up explaining contact strengthening. Okay? The material can't yield because it has nowhere to go. It's already bound to the material surrounding it. And if this ratio of h to x is large enough, or x over h is actually in the exponential, then you get significant strengthening. Okay? So if the joint is thin enough. And so that's contact strengthening. Braze joints often outperform in thin joints in tension what you would expect them to. However, what about in shear? Do you expect any improvement in shear? Not much. Because in shear, if you go through and look at how this all occurs, there's not that same type of constraint here. It's a whole, if you think of the soft material, it's just a deck of cards folding over in shear. So there's not increase in strength in shear. And what about in fatigue? There's probably not a significant increase in fatigue. You expect the fatigue joint to go right down through that braze as the softer material. So contact strengthening doesn't work in every case. But it does effectively, in a joint that's designed for some tension, it does effectively give you some significant increase in strength of a braze joint. Okay? Of contact strengthening? It's basically just the fact that braze joints actually outperform what you would predict otherwise. If you go and look at the base material strength of the braze alloys, you wouldn't necessarily get all of this. It might be 20-30% increase in overall strength of that joint. And so what's the practical industrial application? Really none if you just go out and pull joints and say this is the strength. If you want to scientifically explain why I'm getting that strength, you have to go to understand contact strengthening to realize that it's really there. No, brazes, that's correct. That is correct. Brazes do not do well under shear. However, most brazes are some sort of combination of both shear. They don't perform any better under shear than you would predict from just the strength of the braze alloy. In tension, they do perform better. I guess another practical application is the thinner the joint, the stronger the joint up to some limit, if you want to look at it that way. You don't necessarily, if you want the greatest strength of your joint, you don't fool around with thick joints with lots of clearance. The better the tolerance, the fit up, the stronger that joint's going to be. Yeah.
Does that hold for a strong glue, for a strong adhesive?
It can, but the problem there is you have such a difference in strength that you don't really see it. The glues are often weaker in other ways. That's not always true. It will apply to glues, but I wouldn't say that within the scatter of the strength of the adhesive that you can tell that you've gotten significant contact strengthening. At least I've never seen it. Now, it's true in the glues that as you get thinner and thinner, you can go back to the Stefan equation and explain from a viscous flow point of view. But I would expect in something like a cyanoacrylate, which is a brittle adhesive, if I get thinner and thinner joints, I would expect it to be stronger. And you could try to argue that in terms of viscosity, but I suspect it's contact strengthening just as much. Okay? In general, thinner joints are stronger when you're talking a softer, whether it's soldering or brazing, or was it vibrating? No, okay. Okay. Hey, camera. Anyway. So the practical thing is thinner joints are better, are stronger potentially in most applications, but they're also more expensive to make. So you have to be careful. Other questions?
So this was about the same as when you're passing around those machine stocks with the material in between if they're all solid instead of viscous.
Well, that's sort of what Chris was asking. The machinist blocks show that as you get thinner and thinner, you get stronger joints, but that was argued from you had a liquid in between, and that was viscous flow. When the material gets very hard, it's easier to analyze it in terms of a contact strengthening, which is just a tensile stress on the solid rather than viscous flow. Viscous flow is really a creep phenomena. So you could say that contact strengthening probably explains the joint in short times, and in long times, Stefan equation in creep for a solidified material. And frankly, I guess I can't think of any time anyone's ever separated out the effect of the Stefan equation versus contact strengthening for thin joints. But I do know that thin joints are stronger. You see that from the brazing data, and I've seen, well, I've had opportunities, shall we say, to improve the mechanical performance of joints by basically just designing them so they're thinner, if you can afford to do that. Okay. It does work to make thinner joints. Basically down to about 1/1000th of an inch. I would not necessarily start telling you should go to even thinner joints than that. Okay. Other questions? You start getting down to less than 1/1000th of an inch, you're starting getting problems of fitting the things together. Okay, and you're getting very expensive on your machining costs. Okay, now we're going to actually go into fusion welding or heating, significant heating of things. We're about halfway done with the course, so this is about the right time from my point of view. However, most of my colleagues think this is a welding course, and we start off talking about arc welding and things like that, but that's because they've never taken the course. Remember, if we go back to the two fundamental things that keep bonding from occurring, it's surface roughness and contamination. In fusion welding, we're going to solve both those problems by melting away the surface. We solve both of them because you melt away the surface, you no longer have any surface roughness. You have a liquid surface there. And now you mix that liquid surface with another liquid surface, and any oxides or anything else just float to the top of you got a little micro casting there, a small casting there. So the first half of the course, I keep on bringing up these two fundamental things. Second half of the course, you probably aren't going to hear a whole lot more about surface roughness and contamination. But it's because now I'm just using melting of the base material. I'm still solving those problems, but I'm doing it by melting of the base material. In general, I wasn't trying to melt the base material in any of the things we've talked about in the first half of the course. I wasn't doing that adhesive bonding or soldering. I might have been dissolving the base material in some of the brazing or diffusion bonding things. And actually now let's go back just for a second, because I'm trying to kill the last couple of minutes of time before starting a new topic. There is not a lot of difference between transient liquid phase diffusion bonding and brazing. A TLP bond starts out as a braze and ends up as a diffusion bond as you diffuse away the melting point compressively. So that wasn't the order I presented it in. The reason I presented it in that order, the order I did, has to do more with understanding what's mechanically happening at that interface, and then getting into the liquid phase things such as soldering and brazing. TLP bonding is actually a form of brazing. I actually think that people invented it, quote unquote, for the nickel-based superalloys because they were using these nickel-boron filler metals, which were brazes, which Wall Colmanoid Corporation has built their billion-dollar business off of. And if they left it in the furnace too long, instead of getting a braze out, they got a diffusion bond, transient liquid phase diffusion bond, if you left it in for a few hours. Now, I tried to track that down, but I'd have to go back to 1955, and I haven't found people to confirm that. People in more recent years deny that that's true, but they have a vested interest. They got a patent on it, and they want to think that they thought it up themselves. Okay, I think I've killed enough time, so we'll continue tomorrow when we'll start fusion welding.